So this section is about integrating using cylindrical and spherical coordinates. We just finished talking about cylindrical coordinates, so now let's talk about spherical coordinates. What are spherical coordinates? So how we're going to identify a point in space, how we're going to identify this point here is going to be through three letters, three variables, just as we did before: rho, theta, and phi. And what these three are going to mean, so this rho is the distance you are away from the origin. And that's distance in a true, three-dimensional distance formula sense. And then theta and phi, those are both going to be angles in different ways here. So theta, let me just label X, Y, and Z here. Theta is going to be the same kind of idea as for polar coordinates, cylindrical coordinates. Theta is the polar angle of the projection of your point onto the XY plane. So here's your point, project it down to the XY plane, do theta just like you would for polar coordinates. And then the last one, phi, is maybe the most interesting. Phi is the angle that you are from the positive z-axis. So the first two feel familiar, that theta is the polar angle of the projection onto the xy plane. I mean, that's the same thing as it was for cylindrical coordinates. Rho is the distance you are away from the origin. I mean, r is the distance you are in the xy plane. You have to do some kind of projection. Rho, I should interject here. Rho is a Greek letter, and it's the Greek letter that corresponds to our modern day r. So it makes sense to use that here. And then the weird feeling one is this phi right here. So here's the positive z-axis, whatever angle this is, that is your phi. And so an important point that I want to make here before I say anything else here is I want to talk about natural bounds on spherical coordinates. So we have our, what is going to be, what's a natural bounds of spherical coordinates in absence of other restrictions? So rho is always going to be non-negative. You usually have something coming up there, upper bound rho, but rho always has to be non-negative. Rho can never be negative. And as for theta and phi, theta always has to be between 0 and 2 pi. Just like, for polar coordinates, just like for cylindrical coordinates, that doesn't surprise us. But the one thing that often trips up people is that our bounds on phi run from 0 to pi for our natural bounds, not 0 to 2 pi. So this is a very common mistake. This is a very common mistake that people make, is that saying that phi is something, letting phi run from 0 to 2 pi, or doing anything outside of the interval from 0 to pi. And so I want to emphasize here that if your z is positive, the z value here positive, then phi goes from 0 to pi over 2. If z is negative, phi goes from pi over 2 to pi. So let me just go back to this picture here. If we take this right here, if we're in the xy plane, then the phi is going to be pi over 2. Let me draw another picture here that maybe is useful. I want to draw y and z axis with the idea that the x-axis, the positive x-axis, is coming up at you out of the page here. So if you're up here, this would be phi is equal to 0. Straight up along the positive z-axis is going to be phi is equal to 0. If you're out here, this is like phi is equal to pi over 4. You know, like that angle there is supposed to be pi over 4. If you're along the positive y-axis, this is phi is equal to pi over 2. So if you're along the positive y-axis, or just anything where z is equal to 0, that's corresponding to phi is equal to pi over 2. If you're somewhere down here, this looks like phi is 3 pi over 4. I'm, bisecting this angle here. And if you're straight down, if you're pointing straight down, this is phi is equal to pi. If you're along the negative z-axis, this is phi is equal to pi. Now, the thing that people always would say to me at this point is, well, Matthew, what about like over here? Shouldn't this be like phi is 3? This would be 5 pi over 4. This would be phi is 3 pi over 2. Why don't we do like this? That this is, phi should run from 0 to pi and then back up to 2 pi. Why do we only go phi from 0 to pi? And the idea for that is, if you want to get a point that's like over here, if you want to get to something that's like over here, what you do is that you get to this side of things with theta, and then just do phi is, I guess, 3 pi over 4. So for this one, this is still phi is equal to 3 pi over 4. But the idea over here is that, like, if we're just in literally, now I'm going to just assume that we are x is equal to 0 here. Over on this side of things, this would be theta is equal to 0. Over on this side of things, this would be theta is equal to pi. As positive y-axis, let me make sure I get that right there. No, sorry. That would be if this was positive x-axis, not positive y-axis. This side would be theta is pi over 2, and this side would be theta is 3 pi over 2. So phi always is between 0 and pi. If you just write down integral where phi is running 0 to 2 pi, that's okay. That we just know that that's going to be wrong. Okay, so these are our natural bounds on spherical coordinates. And so the last thing I want to talk about here is how to convert. And so these are our conversions. So x, y, and z, x is rho cosine theta sine phi, y is rho sine theta sine phi, z is rho cosine phi. So note that if we replace rho with r and take off the sine phis, r cosine theta, r sine theta, that matches up with x and y. On the right over here, we also have, so rho is the distance you are away from the origin. Rho is the distance you are away from the origin. So This is our 3D distance formula, square root of x squared plus y squared plus z squared. Theta is defined, it's still the polar angle of the projection onto the xy plane. Tangent theta is still y over x, that doesn't change. And then the last thing that we have here is that cosine phi is z over rho. We're using this rho up here. So these are our conversions. These are good things to know. We'll play around with them in the next video.